Hello, and welcome to this talk on all subgraphs of a wheel are 5-couple choosable. This paper was co-authored with Therese Beadle, and I'm Sambar, a current master's student at the University of Waterloo. In couple choosability, we're given a planar graph, which is a graph that can be drawn in the plane without crossings. And we're also given list assignments for all of the vertices and all of the faces of the graph. The goal is to find a valid coloring for all the vertices and faces of the graph, such that adjacent vertices are assigned different colors, adjacent faces are assigned different colors, and if a vertex lies on the boundary of a face, then that vertex and that face are assigned a different color. We say that a graph is k-couple choosable if it permits a coloring when all lists are of size k. And we moreover define the list coupled chromatic number to be the smallest k such that G is k-couple choosable. More broadly, we're interested in list coloring one-planar graphs, where one-planar graphs are the graphs that can be drawn in the plane with at most one crossing per edge. For a planar graph G, we define x of G to be the graph of adjacencies between the vertices and faces of G. Here on the left we have the complete graph K4, and on the right we have x of K4, where the round vertices and solid edges represent the original graph. The square vertices and dashed edges represent the faces of K4 and the adjacencies between those faces. And we also have dotted edges to represent adjacencies between faces and the vertices which lie on the boundary of that face. From this drawing, we can see that x of G is one planar, since every edge intersects with at most one other edge. In particular, we can see that the edges which intersect are always an original edge of the graph K4 intersecting with an edge representing an adjacency between two faces of K4. In this way, it can be seen that for any planar graph G, x of G is always one planar. Therefore, when we're coupled list coloring a planar graph G, what we're in fact doing is list coloring the one planar graph x of G. Several previous results in coupled list coloring are known. Wang and Lee in 2008 proved that planar graphs are 7-couple choosable, and they also proved that maximal planar graphs are 6-couple choosable. Hetherington in 2014 proved that K2-3 minor free graphs are 5-couple choosable, and it's also been shown that K4 minor free graphs, also known as planar partial 2 trees, are 5-couple choosable. Initially motivated to study planar partial 3 trees, in this talk we prove that every subgraph of a wheel is 5-couple choosable, and that this coloring can be found on linear time. Here on the right we have the example of the wheel graph W9. A wheel graph is constructed by taking a cycle of vertices and connecting all vertices in that cycle to an additional vertex. Throughout this talk we will use a specific labeling for the vertices and faces of a wheel graph. For the center vertex, we will call that x0, and we will call the outer face f0. The cycle we label as x1, x2, x3, and so on, and the interfaces here we will label as f1, f2, and so on. Before proving the result for subgraphs of wheels, we first study the wheel graph itself. Wang and Lee proved that W4, which is the complete graph K4, is 4-couple choosable. Our strategy for the larger wheel graphs is to color the center vertex x0 and the outer face f0, and then color the rest of the graph from there. The rest of the graph is the same as coloring x of wn and minus x0 and minus f0, and we will call this graph x sub n. Here on the right, we've drawn x of w9 and have shown x sub 9 in bold. We have two cases for coloring x0 and f0. Our first case is when the lists of these elements are not disjoint. Because they're not disjoint, and because x0 and f0 are not adjacent, we can pick the same color for each of them. After we've removed this color from the list of every vertex in x sub n, all the lists in x sub n still have at least size 4. In this drawing we can see that x sub n has maximum degree 4. In fact, it's actually 4 regular, and it's also not an odd cycle or a complete graph. Erdős, Rubin, and Taylor proved that any graph satisfying these qualities is always choosable, and therefore we're done with this case. Our second case is when the lists of x0 and f0 are disjoint. We define the set S to be the set of all pairs of colors in these two lists. In this example on the right, the set S will contain the pairs 05, 06, 07, and so on. And because the size of the lists of x0 and f0 are 5, we know that the size of S is exactly 25. For the rest of the vertices and faces of the wheel graph, we define S sub y to be the set of all pairs in S which are subsets of L of y. In this example on the right, for the vertex y star, the set S sub y star would contain the pairs 1, 5, 1, 6, 1, 8, and so on. It wouldn't, however, contain the pair 0, 5, because 0 was not present in the list of y star. And again, because the lists are of size 5, we know that the size of S sub y is at most 6. Our goal from here is to pick some color pair A, B, and S, which does not appear too many times in these sets S sub y for the vertices and faces of the wheel graph. We now upper bound how often some color pair AB will appear as an element in the list S sub y. Summing the size of all of these S sub y's over the vertices of x sub n and dividing by the size of S gives us how often these color pairs appear on average. As shown on the previous slide, the size of S sub y is always at most 6, and the size of S is exactly 25. Moreover, the size of x sub n is exactly 2n minus 2, and therefore we can see that some color pair AB will appear at most n minus 1 over 2 times in lists of x sub n. We will pick these two colors A and B for x0 and f0. And therefore, since the size of x sub n is 2n minus 2, and at most n minus 1 over 2 vertices of x sub n have both A and B in their list, we can see that at most a quarter of vertices had both A and B in their list. In particular, after removing A and B from the list of all lists in x sub n, less than a quarter have 3 colors available, while more than 3/4 of vertices will have 4 colors available. Therefore, since 3/4 of the vertices of x sub n have at least 4 colors in their list, we can in particular assume that f1, f2, x1, and x2 all have 4 colors in their lists. Here on the right, we have the graph x sub 9, where the number in the vertex represents the lower bound of the size of the list on that vertex. We next color the vertices fn-1, xn-1, and x1. In particular, it's possible to show that we can always color these 3 vertices in such a way that f1 has at least 2 colors left. From here, it's not difficult to see that the rest of the graph xn can always be colored. In particular, now we have a path of triangles where all the lists are of size 3 except for the last triangle, which has a list of size 1, a list of size 2, and a list of size 3. It's not hard to see by induction that such a graph can always be colored. And then after coloring all these triangles, f sub 1 will have at least 1 color left. So we have now shown that all wheel graphs are 5-couple choosable. Moreover, if we follow this proof, we get a linear time algorithm for finding this coloring for a wheel graph. We now answer the question of whether we can do better than this, or whether 5-couple choosability is tight. The wheel graph W4 was previously known to be 4-couple choosable, and in fact, we show that this is the only wheel graph that's 4-couple choosable. For wheel graphs on at least 7 vertices, the lists shown here on the right do not permit a coloring. Any choice of colors that we could pick for x0 and f0 leaves some triangle with only 2 colors left in their lists. Here on the right, we've chosen 4 for the center vertex and 6 for the outer face. And here, these 2 faces and this vertex all have 4 and 6 removed from their list. After we've done that, they all have the list 3, 5, and because all these 3 elements are adjacent, it's impossible to color them from there. It can also be shown that the wheel graphs W5 and W6 are not 4-coupled colorable. This, therefore, gives us a complete characterization on the list coupled chromatic number of wheel graphs. We now consider those graphs which are subgraphs of wheels. Unlike in normal graph coloring problems, the list coupled chromatic number is not preserved when taking a subgraph of a graph. Let me give an example to demonstrate this. We've previously mentioned that the graph K4 is 4-coupled choosable. However, the graph K3 has list coupled chromatic number 5. To see this, we examine the graph X of K3, and we see that it is in fact the complete graph K5, since every vertex is on the boundary of every face and both of the faces are adjacent. Therefore, we require that all lists have size at least 5 in order to coupled color the complete graph K3. Let the graph G be a subgraph of a wheel. We now show that G is 5-coupled choosable and this coloring can be found in linear time. We do this proof by case analysis on the graph G. If G is the wheel graph, then we're done since we've shown that wheel graphs are 5-coupled choosable. Suppose that G is the result of deleting a vertex or edge on the outer face. Here we've deleted this edge and we've deleted this vertex. If such an operation has been done to G, then we can see that G is outer planar, since every vertex is adjacent to the outer face. And since outer planar graphs are guaranteed to be K4 minor free, and K4 minor free graphs are 5-coupled choosable, we know that G is 5-coupled choosable. Otherwise, G is a result of deleting edges which are not on the outer face, such as these edges, which we call spoke edges. If at most 2 spokes remain, then G is K4 minor free and therefore 5-coupled choosable. Otherwise, if more than 2 spokes remain, then G is a subdivision of a wheel graph. We now show that subdividing the edges of a graph preserves 5-coupled choosability. Say we subdivide some edge E of G which is incident to vertices UV. And this subdivision produces a new vertex X, as we can see here on the right. In G, E was incident to faces F1 and F2. So now this vertex X is incident to U and V and is incident to F1 and F2. We know that we can color the faces and vertices besides X according to the coloring of G. After we do that, exactly 4 neighbors of X have been colored. And because the list of X has size at least 5, we know that we can always color X after these 4 elements have been colored. Using similar strategies, we can also prove that duplicating edges of a graph to form bigons preserves 5-coupled choosability. And moreover, that adding vertices of degree 1 preserves 3-coupled choosability. To complete our proof that a subgraph of a wheel can be 5-coupled chosen in linear time, we need to be able to show that a K4 minor free graph can be 5-coupled chosen in linear time. The existence of the coloring was previously known, but the proofs did not lead to a linear time algorithm. The idea of the proof is to see that a K4 minor free graph can be built from a tree by duplicating and subdividing edges of the tree and adding new vertices of degree 1 to the tree. Using the lemmas shown on the previous slide, this gives us a linear time algorithm for coloring a K4 minor free graph when all lists are of size 5. So we have now seen that all subgraphs of a wheel are 5-coupled choosable. To end this talk, we briefly examined some graph classes which generalize wheels in one way or another. In particular, we look at Halin graphs, stellated outer planar graphs, and IO graphs. A Halin graph is constructed by connecting the leaves of a tree T in a cycle, as seen here. A wheel graph is a Halin graph where the tree T we start with is a star graph. A stellated outerplanar graph is constructed by taking an outerplanar graph, here shown with circular vertices, and connecting a new vertex x, here shown with a square vertex, and connecting that vertex to every vertex of the outerplanar graph. A wheel graph is just a stellated outerplanar graph where the outerplanar graph we start with was a cycle. We can see that stellated outerplanar graphs are in fact the duals of Halin graphs, and therefore coupled coloring results for Halin graphs exactly translate over to coupled coloring results for stellated outerplanar graphs. What's more, the given example shown here is not 5-coupled colorable, and therefore not all planar partial 3 trees are 5-coupled choosable. This leads us to make the following conjecture that every planar partial 3 tree is 6-coupled choosable. An IO graph consists of an outerplanar graph, here shown with round vertices, and an independent set, here shown with square vertices. An IO graph can be seen as being constructed as a tree of wheels. Here we see the wheels alternately highlighted. Our hope is that our result of 5-coupled choosability for wheel graphs can therefore be extended to IO graphs. Thank you for watching my talk.